So let's start the t-test for two related samples. So as opposed to the last t-test that we did where we were doing independent samples, these are related samples. So this we'll be using with repeated measures designs or with match samples designs. When again, we're either using the same participant in both groups or we're using participants that are matched in some way or related in some way in each of the groups. So this t-test is for, again, these related samples. So again, we're calling these related samples or dependent means t-tests. So again, there's a relationship between the scores in each of the groups, as opposed to the independent means t-test where there was no relationship between the two groups. There was no overlap between them. Just like in our independent groups t-test, however, we have an unknown population mean and an unknown variance, just like in all t-tests. So again, we're going to need to estimate the variance and the population we'll be dealing with again. The means of the population will again be dealt with in the terms of what the difference is expected. Again, we're having two scores for each person in that repeated measures design. We will also be using this t-test for the match samples designs as well. It's the same exact procedure that you used in 3510 for the single samples t-test. So if you I hope have again reviewed that so you're all fresh in your mind, because the only thing that we're changing is that we're using different scores between those two groups to get us to the place that we can calculate using the same procedure that we do for the single sample t-tests. Assume again that the population mean is 0 because we're using different scores. So just as we did in the independent means t-test, we didn't know the population mean for population 1 or the mean for population 2, but we knew that our null hypothesis between those two was 0. We knew that was 0, so that was the number we used. It's the same is going to be true for these related sample means. We're going to assume the difference between the population means is also 0. And so we'll be using 0 for that place. Again, this is a related or correlated sample design. So we're going to use it with the repeated measures, those within subjects designs, where we have John participates in both the control and the experimental condition. Sue participates in both the control and the experimental condition. So those repeated measures or within samples designs. We can also use this for match samples. So again, if we have matched two individuals up on some factor, say it's IQ, say it's level of functioning, any of these things, by creating that match, we've made them related in some way. We again have created this relationship between those two scores. You didn't have an equal chance of being assigned to each group. We've created this relationship, and because we've created this relationship, we're going to be using this related samples designs. Again, the methods are really about the same as they are for those single sample t-tests. We're just using different scores. Again, we're going to have a different number of subjects. Remember that the match subject sample will have twice as many subjects as a repeated measures design. Most of the time, however, the majority of the t-tests we're going to be doing are going to be using a repeated measures design where we have the same person participating in both. But we can, again, use the match samples design for this. And we just have to be really cognizant of, again, the difference between numbers, because a match sample design is technically a between subjects design. So if you need 10 participants in each group, you have 20 participants. Whereas a repeated measures design is a within subjects design. And so if we need 10 people in each group, we can have just 10 people because we'll use those same 10 people in each group. So again, remember that difference between those two when we are calculating our t-tests. So again, the main difference here between the single samples t-test is that we're going to be using different scores. And those are really, really easy to calculate. You do them just the way you think you would. For each person, you'd subtract one score from the other. And then what we'll do is we'll carry out the hypothesis testing just as we would have with a single sample t-test, but now we're going to be using these different scores. So we've done this conversion at the beginning that enables us to use the single sample t-test formulas. Again, we're going to be dealing with this idea of the population of different scores with a mean of 0. So because, again, we're making this comparison, the difference we're assuming based on our null hypothesis is 0. Oh, I'm sorry about that. The t-test, again, is structurally the same as the other t-statistics, except, again, that different scores rather than raw scores. So we're going to be taking those x values that we have for each of our groups, and we're just going to subtract them to get that different score. So there you have the formula that would look like. You take x2 minus x1 and get your different score. And kind of the order in which you do that is somewhat dependent on the hypothesis. If we're looking for an improvement, if we're looking for a decline, those sorts of things. And then we've got our mean difference. We're going to add up the different scores and divide them by the number of different scores that we have. So that's going to be calculated in the same way. And then once we have this mean difference scores and these different scores, we're just going to treat those as now our raw data. So we're going to use, once we have those different scores, that's going to be the data that we're going to be working with. We're no longer going to be working with those raw scores X. We're going to be exclusively working with these different scores. So again, the T formula you can see is exclusively dealing with different scores. So we're talking about mean difference minus the population difference, which again we assume to be 0 based on our null hypothesis. We're going to be dealing with then the estimated standard error for the mean difference scores. And we'll get that by calculating sums of squared based on our different scores. We're not going to do them individually. We're going to do them with our different scores. So you can see how this is going to be a lot quicker to calculate than the independent groups, where you had to calculate a sums of squared for group 1 and a sums of squared for group 2. Here we're going to, once we get those different scores, only calculate the sums of squared for those different scores. And then those values will be plugged in to the formulas that, again, should be pretty familiar, and we'll use them accordingly. So again, the structure of all these things are the same as the single sample t-statistic. So if you're not really strong on that single sample t-statistics from 3510, I really recommend you going back and reviewing your notes, going back and reviewing the text, and there is again an overview slides that you can look at on D2L on that as well. Because if you're a little rocky here, it's going to be hard to make that that jump to these t-tests for the related samples. So here's how we would do those different scores. For subject A, again, subject A participated in condition 1 and condition 2. So we have 2 scores, 10 and 14 for participant A. So we'll take 10, we'll take 14 minus 10, that gives us 4. The same thing for participant B, we have 2 scores, 13 minus 15, that gives us negative 2. Participant C, 15 minus 12, that gives us 3. And participant D, 12 minus 11, that gives us 1. So we have these different scores, and once we have these different scores, we're no longer going to look at the raw scores in group 1 and group 2. We're only going to be dealing with these different scores for our t-statistic. Again, the population of different scores we're going to assume to be 0 because of our null hypothesis that there is no difference between those groups. The same will be true in these related repeated measures and related samples t-tests as it was in the independent groups with directional hypothesis and non-directional hypothesis and one-tailed and two-tailed tests. All of that is the same. So, and the same will be true of our hypotheses, our null hypothesis and our research hypothesis. That will all be the same, just as it was for the, again, the single sample t-test. So again, the only change here is this difference score. This slide is showing you the new thing that we're doing, these difference scores. So again, the numerator of the t-statistic is going to measure the actual difference between the mean difference scores for our sample versus the hypothesis of mean difference scores, which is again 0. Our null hypothesis is that there is no difference. So that numerator is again where our signal is. We're saying, okay, we're trying to see how different we are from 0, how different our different scores are from 0. That's where our signal is. The denominator measures that standard difference that is expected if the null hypothesis is true. So once again, we're dealing with that standard, that estimated standard error that we would assume to have if that null hypothesis is true. This is again our noise. We're dividing our signal by our noise, what that variance is, to kind of find out if this signal really is truly a signal or not. And we'll have the same 4-step process as other tests. We're going to need to calculate degrees of freedom, and we're going to need to figure out the cutoff and the critical regions for this null hypothesis testing. Again, the same rules are going to apply for directional hypothesis and non-directional hypothesis and 1- and 2-tailed tests. So all of this will be the same. So if you looked at your t-table and you looked at degrees of freedom 8 for an alpha level of 0.05, you would see for a 2-tailed test negative and positive 2.306. So again, that would be the value you have. Again, here we're going to be dealing with degrees of freedom based on the number of participants. So again, make that distinction between matched subjects and repeated measures designs, those within subjects designs, to make sure you're dealing with the proper N before we get started. So here are the learning checks, just to make sure. Again, there really wasn't much new here except those different scores, so this is really pretty straightforward. So let's read the learning check. Pause the video, figure out the answer, and then proceed on. So for which of the following would a repeated measure study be appropriate? A, a group of twins is tested for IQ. B, comparing boys and girls' strength at age 3. C, evaluating the difference in self-esteem between athletes and non-athletes. Or D, students' knowledge is tested in September and tested in December. Then again, ask yourself that same question, but ask it for a matched subjects design. So remember, the repeated measures study is going to be looking at those within subjects designs, and the matched subjects study is looking at a between subjects design where we've matched individuals in some way. So pause the video, figure out the answers, and proceed to the answer slide. So for the repeated measures design, the answer is D. We're testing students' knowledge in September and December. We're getting 2 data points from each individual. For a matched subjects design, the answer is A. A group of twins is studied for IQ. This is the matched example. Again, because it's a pair of twins, they are related in some way. So this is a related sample. Twin A and twin B would be in separate groups, and we would compare those. True or false? Decide which of the following is true or false. True or false, a matched subjects study requires only 20 participants to obtain 20 scores in each of the conditions being compared. True or false, as the variance of different scores increases, the magnitude of the t-statistic decreases. So again, look over both of these, decide which one is true and which one is false, or if they're both false or both true. Pause the video and proceed to the answers. The first answer is false. A matched subjects would require 20 additional subjects because, again, we'd have 20 in group 1 and 20 in group 2. Remember, a matched sample, we are dealing with a between subjects design. And for the second one, increasing the variance increases the denominator and decreases the t-statistic. Remember, the variance is that noise. So if we put more noise down there, that's going to weaken our signal. It's going to be harder to detect our signal in more noise. So it's going to lower that t-statistic and make it not as high. I hope that was helpful. We also have a slideshow that I put up as well that has a sample problem that you can look through. And then again, there are examples both from Dr. Good on D2L for you to watch, and there's some practice problems for you to work on. We'll continue to work on this and add in effect size on Wednesday. Thanks.